One of the things we do with Lewis dot symbols is use them to help us predict the way two elements will come together and bond. And that's what we're going to be working on this worksheet. So first question, we want to predict the compound that's formed between potassium and fluorine. To do that, we're going to begin by drawing the Lewis dot symbols of each. Potassium is in the first column on the periodic table, which means in its Lewis dot symbol, it just has one electron, one valence electron. And fluorine is in the 7th column on the periodic table, which means its Lewis dot symbol has 7 dots for those 7 valence electrons. Now, when these two atoms or any two atoms come together to form a compound, they have this overall goal of either creating a situation where they have a total of 8 electrons around them in their Lewis dot symbol, or they have no electrons around them at all. So the goal here either is to get like a perfect set of 8, we call that an octet, or to just strip away all of the electrons completely so that there's just nothing there in that valence. And they accomplish this by shifting electrons around, by basically passing them back and forth. So when we look at, let's say, potassium, what can we do to make potassium happy? Remember, the goal is to either create this octet where there are 8 valence electrons around potassium, and we could accomplish that by taking and adding 7 electrons to potassium. That would take a lot of work because that's a lot of electrons. The other thing that we could do is just get rid of potassium's electron. In general, we find that atoms will do whatever they can that involves the exchange of the least number of electrons. So getting rid of 1 electron is much easier than adding 7 more electrons. So this potassium is going to get rid of its electron. Now let's think about fluorine. What does fluorine want to do? So fluorine's option is going to be to add 1 more electron, or to get rid of all 7. And again, it's going to choose to do whatever involves the exchange of the least number of electrons, which means we want to add an electron. So this is a perfect situation here because the potassium wants to get rid of an electron and the fluorine wants an electron. And so we'll see that exchange just happen directly, where the potassium is just going to move its electron over to the fluorine. Now that's going to give us a potassium that's lost its electron, which means it's going to be an ion, positively charged ion, and our fluorine, which is now going to have 8 electrons instead of 7, that fluorine has gained an electron, so it's got a negative charge on it. It's an anion. And this is the compound. This is one of the ways that we can represent the compound that's formed. The way that we would write this in terms of a molecular formula or a formula for a compound is just Kf. And the reason that we write it this way is because we know that it takes 1 potassium atom to make the fluorine atom happy, the exchange of 1 electron. Let's practice this again. Next question, we have magnesium, which is in the 2nd column, which means that it has 2 valence electrons. And then we also have sulfur. Sulfur is in the 6th column, so that means it has 6 valence electrons. So let's think about what these atoms want. Magnesium wants to get rid of its 2 electrons because that's easier than adding 6. Sulfur wants to pick up 2 electrons because that's easier than getting rid of 6. So again, we have another perfect partnership where the magnesium can transfer both of its electrons over to sulfur to give sulfur all 8 electrons. Magnesium, after this is done, the magnesium will have a 2+ charge because it's lost its 2 electrons. The sulfur will have 8 electrons around it, and the sulfur, because it's picked up 2 electrons, it has a 2- charge. The formula for this is going to be Mgs, 1 magnesium required to make that sulfur happy. Next one, we're going to try sodium and oxygen. We're already on oxygen, so let's draw that Lewis dot symbol first. Oxygen, like sulfur, has 6 valence electrons. And then sodium, on the other side of the periodic table, sodium has 1 valence electron. So what do we want to do here? We want to get rid of this 1 electron on the sodium. We want to add 2 electrons to the oxygen. Now the sodium is only capable of adding 1 electron to the oxygen, even though oxygen wants to. That's okay. In a situation like this, we're not restricted on just 1 of each type of element. So we could bring in a 2nd sodium atom if we wanted. We could even bring in a 3rd if we needed it. And this is going to give us a sodium cation, positively charged ion, an oxide anion, so that oxygen now has 8 electrons, it has a 2- charge, and then there's that other sodium cation as well. 2 sodium ions, so that needs to be Na2 with the oxide ion, Na2O. And we have one more. We have magnesium, which has, we've already drawn this one, has 2 valence electrons, and phosphorus. Phosphorus has 5 valence electrons, 1, 2, 3, 4, 5. The magnesium wants to get rid of its 2 electrons, so there's 1 and there's 2. The phosphorus still needs 1 more, so just like we saw in the previous example, we can bring in another magnesium. And there is phosphorus's last electron, so that phosphorus is happy, but now we have this situation where we have a magnesium that needs to get rid of another electron. That's fine. We could bring in another phosphorus atom. We can bring in as many atoms as we need. So now this magnesium can transfer one of its electrons to the second phosphorus. Now the phosphorus, again, is still a little unhappy. It needs some more electrons, so we'll bring in another magnesium. I'm going to draw my dots in different spots this time. And now, finally, we've got all of the atoms happy. What this will look like is a magnesium cation, 2+, because it loses 2 electrons, with a phosphorus anion. That phosphorus picked up 3 electrons, so it's a 3-. Then we have another magnesium cation and another phosphide anion, and then one more magnesium cation. Altogether, 3 magnesium, so we're going to say Mg3, and 2 phosphides, P2.